The famous Italian monk Giordano Bruno in 1586 published a book in which he said the sun is a star and that the Earth was a planet and that other stars certainly had planetary systems and probably even had life. And for that and other radical things that he said, the church burned him publicly. You could say that extrasolar planets was a much hotter field back then.
Exoplanets were almost as silly as looking for extraterrestrials, you know, little green men on other planets.
Seriously, looking for planets was a kind of weird topic.
The whole field had sort of a snake oil sheen about it because over the previous 50 years or so, there had been many, many claims of the first extrasolar planet ever. And the one thing all those claims had in common was that they were wrong.
In San Francisco, California, astronomers Jeff Marcy and Paul Butler were quietly looking for Doppler shifts, changes in the observed color of light from the star.
I literally spent the first 8 years of the program simply trying to improve the techniques involved in making these sort of measurements, mostly totally under the radar. Nobody knew what we were doing and nobody cared.
A ray of hope that it might be possible to detect a planet came with the discovery by Dave Latham and Svi Mazet of a mysterious object orbiting the star HD 114762.
They announced the detection of an object that they called a brown dwarf. They looked and they didn't see it in a telescope, so if it was a star, if it was 1,000 times the mass of Jupiter, they would have seen it.
To this day, it is not known whether this object is a planet, a brown dwarf, or even a low-mass star, but its discovery emboldened others to continue the search. A different and dangerous approach to planet hunting was underway in Canada. The team of Gordon Walker and Bruce Campbell employed the deadly gas hydrogen fluoride in an attempt to precisely measure Doppler shifts.
And he showed me their setup in Canada at one point. One person would be in there doing the setup, and the other person would be outside of the room looking through a porthole with 2 gas masks. And his job was, if something went wrong, throw on a gas mask, run into the room, throw the gas mask on the other guy, and drag him the hell out. Any good science should have an element of danger. There should always be at least the vague hint of death involved. Otherwise, you're not really on the cutting edge. They really pioneered the whole field, just a spectacular achievement.
We're all here because of the work that they did.
In 1992, another incredible discovery piqued the interest of astronomers looking for exoplanets. But these new exoplanets were not orbiting a regular star. They were orbiting a pulsar.
2 very small bodies got detected at Arecibo by Wilsham and his colleagues, and they really got us scratching our heads. So we call them pulsar planets.
Wilsham and Frail is somewhat of a special case because I don't think anyone really doubted that these were planets as much at the time, but they were planets around a bizarre object, a pulsar.
But they really were the first 2 bodies to orbit a dead star, not a currently shining star.
The formation of planets is an incredibly robust process, and that's what that discovery told us, and we missed it because we didn't understand it.
We should have understood that planets don't come in ones, that they come in systems, but we were still focused on finding the very first planet.
Halfway around the world in Geneva, a pair of Swiss astronomers were hard at work developing a different technique. Their instrument relied on fiber optic technology, and they used it to turn their eyes on exoplanets.
My first day of work, I got this booklet from Michel that was the ultimate knowledge of data processing of spectroscopy. There was almost nothing at that time, and that's it. And we had to to do this instrument. And we designed this practically without much support from anybody else, because the other people felt that this was not interesting.
After a few months, already at the end of '94, we got a signal of variability for several stars, not only one, several stars.
We realized very rapidly that the instrument could be far more precise than we thought. So I started with a couple of stars a bit more intensively, and 51 Peg was one of them because it was bright. And very rapidly, 51 Peg had a very weird behavior.
On one side, we were absolutely sure of the quality of our measurement. All the signal was in favor of a planet, but it's evident it was a so unusual planet.
And I really thought at that time, oh, there is something really bad in the software on the instruments, and I better to figure out, because otherwise my PhD would be compromised.
Over the next several months, the two astronomers checked and rechecked their data. The problem was no one could imagine a giant planet with such a short orbit.
So we came back in July, this time together with Michel, very excited. I say, okay, let's see whether the conclusion that we had with the first bunch of data we had still holds.
The real moment where we had the confirmation of the reality of 51 Peg, it was really a planet, was in July '95.
First data, just on it, we say, okay, just luck. Second data, still on the curve, we say, okay, well, 2 is far, but still 2 is not enough. The third one was still on it, following a track, and then we say, well, let's just wait the fourth to be really, really sure, because it was so embarrassing conclusion, that planet, that we really want to make sure that was real.
We got the good period, the good amplitude, and so on. So at the time was really the time for the celebration. Before we were not sure that it was a planet.
I mean, there is a real planet. Believe it or not, there is no theory to predict that planet, but there is a planet there.
Following days of rumors circling the globe, at a conference in Florence, Italy, the news unofficially leaked. A Jupiter-sized planet had been discovered. This massive planet was making a complete orbit of its star in only 4 days. How could that be?
Suddenly there's this 51 Peg, which is a Jupiter-sized planet, but in a 4-day orbit. Well, people knew that was impossible. If Jupiter-like planets orbit at like Jupiter and Saturn orbital distances.
Back in San Francisco, Marcy and Butler, by mere coincidence, had 4 consecutive days of reserved telescope time at the Lick Observatory, the exact amount of time needed to confirm or debunk the claim.
We hit the star very hard for those 4 nights. We reduced the data as quickly as we can. We were blown away. We saw exactly the signal that Mayor and Collot had announced.
Confirming my data, to me, was just the best gift I could have had, because I said, oh, fine. So all the work I did is...
Space station crew returns safely to Earth. Practice for our asteroid sample return mission, and a new discovery from old data. A few of the stories to tell you about this week at NASA. On April 17th, our Andrew Morgan, Jessica Meir, and Oleg Skripochka of the Russian space agency Roscosmos said goodbye to the International Space Station's Expedition 63 crew, including our Chris Cassidy. Several hours later, Morgan, Meir, and Skripochka landed safely in Kazakhstan. Morgan spent 9 months on the station, while Meir was on board for about 6 months. During that time, she conducted the first 3 all-woman spacewalks with NASA's Christina Koch. On April 14th, we conducted the first practice run with our OSIRIS-REx spacecraft in preparation for its attempt this August to collect a sample from asteroid Bennu and safely return that sample to Earth. The rehearsal, known as Checkpoint, placed the spacecraft the closest it has ever been to Bennu. This is NASA's first ever sample return mission to an asteroid. Old data from our Kepler Space Telescope, which was retired in 2018, has led to the discovery of an Earth-sized exoplanet in its star's habitable zone about 300 light-years from Earth. Out of all the exoplanets found by Kepler, this distant world, called Kepler 1649c, is most similar to Earth in size and estimated temperature. The 50th anniversary of Earth Day is April 22nd. To help observe the anniversary virtually in this new world of social distancing, we have put together new and curated online videos, activities, and other resources at nasa.gov/Earth Day. Some of the material is available in both English and Spanish. We also encourage you to use the hashtag Earth Day at home to share images showing what you did to observe Earth Day. NASA is looking for help from video gamers and citizen scientists to map coral reefs around the world. Participants will play a video game to identify and classify corals while virtually traveling in an ocean vessel. The game, called NemoNet, which is available for iOS devices and Mac computers, uses 3D images of the ocean floor, corals, algae, and seagrass taken by specialized NASA instruments mounted on drones or aircraft. Data from NemoNet will eventually enable NASA's Pleiades supercomputer to map out the world's corals at an unprecedented resolution. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
Here in San Francisco, the discovery was dramatically verified just this past weekend.
October 19th, 1995.
What may be the discovery of new planets outside our solar system has created enormous excitement among astronomers.
The confirmation was made before the official announcement of the discovery itself.
It went completely out of control.
Everybody was discussing of this new object except us.
By tradition, scientists have their discoveries peer-reviewed by other scientists for accuracy.
I was one of the referees on the paper. There were 3 referees, and normally I think they only do 2, but this was so big that the Nature editor, Leslie Sage, was being very careful.
Because of the situations, Nature was very strict. They say, well, look, guys, if you talk to people, then we're not going to publish your paper.
So it's only after 1 month or something like this that I receive a message from Nature that, okay, no, you are relaxed from the embargo.
Because the discovery was just too big, just far too big to follow the usual scheme that is required for a scientific paper. As soon as you start talking about that, I mean, everybody wanted to know about this.
51 Peg B is a real planet, no question about that.
As soon as we detected 51 Peg, he had on his data plenty of something like that. You just need to look at it.
At this point, we hadn't analyzed all our data. We had 2 computers, and it would have literally taken us 5 or 6 years to get through all of the data. So literally about a half a dozen different groups said, you know, we've just received these new computers, and we're not going to use them for the next several months. You want to dump your jobs on it.
Within 2 months, 2 other Jupiters circling around their stars were found by Marcy and Butler, and the floodgates of planet hunting were now wide open.
You know, from no planets at all to the point where we're discovering a new planet every month or even sometimes every week. And almost all of the planetary systems that we found were very different from the solar system, weren't even similar in the least bit.
I remember asking at a meeting, you know, how long do you think this will go on? And I think Michelle Mayor said, oh, maybe, you know, another 5 or 10 years, and then the game is over. Fortunately, the game just got a lot more exciting.
After getting my PhD, I became aware of this fellow at NASA Ames Research Center, Bill Barucki.
I would see him at all these meetings. They were very small meetings back in the day. And like he'd literally be by himself out having dinner, so we would join him and chat about things, and he was very persistent.
Bill walked around the halls, and whenever the Ames managers saw him coming, they turned and walked the other way.
Bill Barucki wrote a paper in the 1980s that described the transit method. When that planet passes in front of the starlight drops by a tiny, tiny amount. And by measuring the brightness of the star minute by minute, we can detect planets going in front of the star, and we call that the transit method. And detectors that could measure that precise drop in brightness didn't exist yet.
To be successful, all one needed to do was build a photometer 1,000 times better than anyone ever built one. But I'd worked on the Apollo program, I'd worked on other programs, so that's not really that scary. You just need to get down to brass tacks and find out what's required and build it. There just is no way of finding small planets in orbits like that of the Earth unless you go into space. You must go into space.
He kept getting shot down by the review panels for various reasons, and each time he'd fix the reason and go back a second time, and they basically said it's not going to work. Well, Bill Barucki didn't bother reading that report, or at least he did not take it to heart. He kept on his crusade to show that transit detection should work.
He was able to demonstrate in the lab that he could measure the precision required to find Earth-sized planets orbiting sun-like stars.
Some people call it stubbornness, but the point is I knew it would work.
So he proposed and reproposed, and eventually he conceived of a Discovery-class mission that was later called Kepler.
It was 25 years between the date of publication and the date that Kepler actually launched.
1-0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Kepler just delivered so much tremendously new things we never even conceived of. And the things that were on our wish list, Kepler found for us.
This data was being displayed for the first time on the computer monitors. And there was the transit of that Jupiter-sized planet, and the data was like beads on a string.
Kepler has transformed our understanding of exoplanets. What Kepler was designed to do specifically was to go after terrestrial or rocky planets that are in closer orbits to stars. We now know from the Kepler data that planets like the Earth are in fact common in the galaxy, and that's something we fundamentally didn't know before Kepler.
The first exoplanet was already diverse, and Kepler continued to find more and more planets that didn't fit the norm, both in size, in composition, in distance from their stars. So when you think about how many stars there are in our galaxy, there are a few hundred billion, and if each one has one or maybe more, we're looking at a few 100 billion planets.
To accomplish something great, you have to have persistence.
To succeed in exoplanets, we have to be very ambitious and very bold.
Kepler's impact was extreme, certainly more than I'd ever imagined. It's basically opened up an entire new era of astronomy.
Now that we know that the galaxy is teeming with planets, we are ready to go to the next chapter of planetary exploration.
I truly believe that the 2020s are shaping up to be a golden age for observational astrophysics. You know, we have these amazing telescopes like TESS, the Transiting Exoplanet Survey Satellite. We have WFIRST, which is this Hubble-sized telescope that can see 100 times as much of the sky in each image. We have the James Webb Space Telescope, which is, you know, the largest and most powerful telescope we've ever built. You know, the reason that we can even dream about that and create something like that is because of the success of Spitzer and Hubble and the previous great observatories.
I'm looking forward to space-based missions where they're going to have coronagraph technology and maybe even star shield technology in order to image exoplanets by blocking out the light from stars.
And we have the next generation large 30-meter class telescopes on the ground, which are going to be coming online in the 2020s. But the question that has me most excited about the future of astronomy is to answer the question, are we alone in the universe?
Finding evidence of life on an exoplanet, finding an indication of a living world is within our reach.
What is life? Life is a process to transfer information from one generation to another.
Everybody is interested in the search for planets, the search for places that remind us of home.
We're looking for some hint of our origins, where we came from, and exoplanets may very well provide that context.
There may be more habitable real estate out there beyond our solar system than we once thought.
I think we're naturally curious to find out if there are other conditions in the universe that might be similar to our own. And finding exoplanets around other stars is the first important clue.
The search for planets is a search for life. And even though we didn't really say that out loud, that was always in the back of our minds.
My land-covered career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything, because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Dr. Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I use satellite imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are made up of a series of pixels to show what covers the Earth. A pixel, or picture elements, is the smallest unit of a digital image. When combined with thousands of other pixels, a picture is formed. Each pixel color shown represents a land cover type. It's from these pixels where ground verification or ground truthing come into play. You see, depending on what satellite is taking images, a pixel can cover roughly an area of 30 to 500 meters squared. For imagery captured by Landsat, a pixel is 30 meters squared, or about the size of a baseball diamond. However, part of that pixel showing forest might actually be water, or shrubs. By taking land cover observations, Citizen scientists can help answer these questions when it comes to land cover maps. So, why are these land cover observations so important? Why are they taken in the first place?
We also are looking at how these components are changing over time. So deforestation in the Amazon or across the world, how are cities expanding? A lot of different things to study, and really the view from space is the way that we do it here at NASA. We have big supercomputers that simulate the physics of the atmosphere and the land, the interaction between the Earth systems. It's important to have that, that land cover map. It sets certain parameters. Those models can actually be used to look at current day conditions and weather. So based on these current conditions, what might the Earth look like 50 or 100 years from now? There's an element of understanding, but then also being able to predict into the future, what that might be like, what these changes may mean for us.
Each point shown here represents a real-world measurement of environmental conditions. Scientists use computer models to fill in information where measurements may not exist. By verifying the satellite imagery and using the data for these models, scientists can predict changes in our environment more accurately. One of these scientists using land cover maps to track urbanization as part of her work is Dr. Amita Mehta of NASA's Goddard Space Flight Center.
So urbanization changes terrain as well as characteristics of the surface itself. And so impervious surface is what we look at when we are monitoring flooding. When there are, say, parking lots or cement and concrete surfaces, they increase. So previously, if it was a farmland or something which was not built, and if that is built now, that water previously that could go or percolate in the soil and in the ground now cannot go in, and it stays there. Monitoring helps you to plan for it. So if you see land cover changing, even then you know that how water is going to flow in that region might change. If you have to send rescue out or you have to plan for relief activities, then if you know land cover, then you know where there might be help needed.
By using land cover maps and models that reflect changes over time, scientists can predict where flooding and other events may occur. With a changing climate, these predictions from models and land cover maps can help scientists better understand these changes and help communities prepare for them. But perhaps a more important reason as to why take land cover observations is you get to participate in a community of scientists, citizen scientists, and students.
So it's a very important component that the citizen science and students of the GLOBE program and GLOBE Observer can contribute to, is by really giving us the information on the ground of what they're seeing around them and in front of them. And we hope over time as well how maybe some of these things are changing, because those would be very valuable for science.
I saw the value of having information before a hazard happens, because once that fire went through an area, we can never recreate that data. This is all important for us to share and put together, because that's how we understand Earth as a system. All of these things end up affecting where we live, why we live where we do, and why we make some of the choices that we do.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.